Hey everyone, in this AP Chem series video, we're going to start taking a look at the periodic trend in atomic radius. You may or may not already know that the periodic table is full of patterns and recurring variations like that in valence electrons based on column shown in green or in charge shown in red. Whenever there's a pattern or recurring variation in certain element properties, we call that periodicity, and sometimes it's also called periodic trends, which is actually the term that I'll use more often in these videos. It's a good idea to have this definition for periodicity written down somewhere, so try and do that before we move on. In this video, we'll start learning about one property where periodicity exists called atomic radius. Atomic radius is defined as the average measurement from the center of the nucleus to the boundary of the outer electron shells. Essentially, it's the radius of the atom like I've got shown here on magnesium. It's sometimes referred to as atomic size because an atom with a larger radius is going to be a larger atom. It's also measured in super teeny tiny distance units called picometers, like magnesium's 150. Now let's get into the important stuff here. Atomic radius will change predictably based on the attraction of the outer electrons to the nucleus. So if there's an atom with a very weak attraction between that positive nucleus and those outermost electrons, it's going to be much larger. If the attraction was stronger, however, it's going to pull those electrons in closer and result in a smaller radius. An even stronger attraction would have an even larger effect and produce an even smaller atom. To summarize that, we could say that a stronger attraction results in a smaller radius, or a weaker attraction, a larger one. That's definitely one of the key ideas for this video. Make sure you've written it down. So let's finally get to the periodic table and talk about this trend and the patterns that exist for atomic radius. In this video, we're only going to focus on the trend across a period or a row on the periodic table just to keep things simple. We're also going to ignore these transition metals, focusing only on the representative elements. Let's make them go away completely. Lastly, I'm going to randomly choose row number 2 to focus on. Everything we say for row 2 will be true for all the other rows on the periodic table also. Before we get started analyzing the trend, I'm also going to bring back two older pieces of information, one from the start of this video on how to make predictions about an atom's radius. The other is from the previous video on Coulomb's law. So let's finally go back to row 2, and you can imagine maybe moving from left to right across this row, starting with the element lithium. For each atom in the row, there's two things we're going to want to analyze. The first is its nucleus and the corresponding nuclear charge. Lithium's is +3. The second is the electron configuration. So we don't have to do this for every single atom. Let's skip over to boron and then nitrogen and end with fluorine. So here's some important things to notice about these atoms. The first has to do with those outermost valence electrons. They're all in exactly the same energy level. Because there's no differences in highest energy level for these atoms, we can't use that to explain any size differences. At the same time, we can see that all of these atoms also have the same amount of core electrons, meaning the shielding is approximately the same across the row as well. So within a row, it seems like the electron arrangement is essentially the same. That means the only major differences between these atoms is going to have to do with their nuclei. Let's now compare the nuclear charges and effective nuclear charges of these atoms. In lithium, there's a +3 nuclear charge with 2 shielding electrons canceling it out, meaning the effective nuclear charge is +1. In boron, the effective nuclear charge is +3, nitrogen +5, and fluorine +7. So finally, we have something different about these atoms. The nuclear charges and the effective nuclear charges increase as we move left to right. This increased charge magnitude, go back to our statement from Coulomb's law, results in a stronger attraction between these outermost electrons in red and that nucleus. That stronger attraction results in the electrons being pulled closer to the nucleus and a smaller radius. We can see that effect in these actual measurements of the radii for the atoms in row 2. Let's try to summarize these ideas and put it into some words that you can jot down if you think you need. In general, you'll see that atomic radius will decrease from left to right across a row. Since the outermost electrons fill to the same energy level, these size changes are due to the increase in nuclear charge and effective nuclear charge. As those nuclear charges increase, there's a greater attraction between the outermost electrons in the nucleus, resulting in smaller atoms. These are definitely some key ideas for this video. Make sure you jot them down. That also wraps it up for Atomic Radius Part 1. Thanks for watching, and here's a brief summary.